So I've just finished lecturing on eigenvalues. It's a very exciting topic for me. I love eigenvalues. And now I'd like to show you a few things involving Sage regarding what we've said so far about eigenvalues. So the most important takeaway from the lesson is just what is an eigenvalue? It's a number lambda, so that lambda times the identity minus A is a singular matrix. It's hard to get much further without understanding that initial starting point. So what I've written here is the first piece of Sage code I have is just the syntax we would use to directly verify this. So if we start with a number, which I'll call L here, and a matrix A, and we want to verify whether or not L is an eigenvalue of A, what we want to do is we want to look at L times the appropriately sized identity matrix minus A, and then figure out the rank or the nullity of that matrix. So if you input any n by n matrix on the first line here called A, and then you define L to be any number here, this code will spit out the matrix A in this first print statement, so you can verify that you input the right A. And then this will give us the reduced row echelon form of the associated characteristic matrix. And the idea is that we can use that to figure out whether or not our lambda was an eigenvalue. So let's click evaluate and see what my default code runs as here. So here I input some particular 3x3 matrix A. So you can see the numbers here are kind of gross. And the L that we input was 9. And so what we're doing is we're trying to figure out if 9 is an eigenvalue of A. And it looks like the reduced row echelon form of 9 times the identity minus A is equal to this particular matrix. And here we see we only have one pivot. The rank is less than the size of the matrix, which is 3. So that tells us that 9 is an eigenvalue here. Alternatively, you can see that the nullity is 2. There are 2 non-pivot columns. So that tells us, since 2 is bigger than 0, that 9 is an eigenvalue of A. If I messed around here, so if I put 10, let's see what happens. So I'm changing L from 9 to 10. If I click evaluate, I see that the reduced row echelon form of 10 times the identity minus A is equal to the 3x3 identity matrix, which has rank 3, and therefore, since the size is 3, is non-singular. So 10 here is not an eigenvalue of A, but 9 is. And remember from lecture, being an eigenvalue is very rare. So if you just start to input random numbers for L, you're almost never going to get an eigenvalue unless you're lucky. So you could be more efficient here. So here I'm advocating for like a method of computation that still makes us do a little bit of work. So if we are good at interpreting what reduced row echelon form is, we can use this quite well. But you could also tweak the code and just directly ask, is the characteristic matrix singular or not? And the syntax for that would be L times the identity matrix minus A, and then you would use dot is underscore singular. So here I have the same code, except I've adjusted to just directly ask, is this number an eigenvalue? So if you click evaluate here, you'll find I have the same predefined matrix input here, and we're asking, is L equals 9 an eigenvalue? And the answer is true, or yes. Again, if I change 9 to 10 here and click evaluate, is L equals 10 an eigenvalue? False is what it's telling me, or no is the answer here. So this is maybe a less, this is a valid way of doing it, but it maybe takes too much of the work off of us while we're learning. But I figured I'd put it here anyway. And finally, remember the last part of the lecture was this discussion of geometric multiplicity. The geometric multiplicity of an eigenvalue is the nullity of the associated characteristic matrix. So remember in Sage, the right syntax to call the nullity of a matrix is right underscore nullity. So here what I'm doing is I'm saying, well, to figure out the geometric multiplicity, we input L times the identity matrix minus A, and then we hit dot right nullity, and that will give us the geometric multiplicity. So I have my same example predefined in here, and if we scroll up and remind ourselves what happened in the original example when we checked whether or not L equals 9 was an eigenvalue, we found that the characteristic matrix was 3 by 3 with rank 1, so the nullity was 2, which means the geometric multiplicity is 2. I can go down here and I have the same example predefined. If we click evaluate, it tells us that the geometric multiplicity of 9 as an eigenvalue equals 2. So that's sort of a direct way to do it. Really my intent here is, well, we have this direct way, but I also want us to understand why it's 2. And the reason this number is 2 is because when we went to the characteristic matrix in row reduced, we had 2 non-pivot columns. So these are some basic calculations we can do to familiarize ourselves with this concept of an eigenvalue and this idea of geometric multiplicity. There's going to be plenty more that we do with eigenvalues as the semester progresses, but I think this is a really solid starting point.